Welcome to The Sleepy Scientist. I'm glad you're here. Whether you're tucked under the covers, curled up on the sofa, or simply letting your thoughts drift like dandelion seeds on a breeze, you're in the right place. This video is all about the nature of mass, what it is, how it behaves, and why it matters. It's a journey through gravity, particles, and cosmic fields, all wrapped in a gentle voice to help you relax. Now, I do hope this video isn't so interesting that it accidentally ruins your sleep, but if it keeps you up just a little longer, well, at least you'll leave with a new fact or two to impress someone over tea tomorrow. Before we dive in, I'd love to know where in the world you're watching from. Are you listening from a quiet corner of New Zealand, a snowy Canadian night, a warm room in Brazil? And what time is it for you right now? Let me know in the comments below. It's always lovely to see the sleepy little constellation of listeners from all around the world. If you enjoy this calming blend of science and storytelling, please consider leaving a like and subscribing. It helps the channel float gently through the vast algorithmic ether and reach more sleepy minds like yours. Tonight we're exploring something deceptively simple. Mass. It's everywhere. It shapes our lives, and yet the more we study it, the stranger it becomes. So take a deep breath, let your body settle, and allow your mind to drift as we begin. Just a gentle reminder, this video is for relaxation and educational purposes only. It is not intended to diagnose, treat, or cure any medical conditions, including insomnia. For that, please speak with a qualified medical professional. You know that moment when you try to lift a suitcase and instantly regret your life choices? That quiet little protest from your muscles, that's mass. It's not shouting, it's not flashy, but it's always there, making its presence known every time you pick up your grocery bag, plop down on the couch, or try to slide your sleeping cat off your laptop. Mass is the silent partner in every action involving matter. And yet, for something so ever-present, it's surprisingly slippery when we try to define it. Let's start with something deceptively simple: weight. Most people use mass and weight interchangeably, but in physics they're as different as a chocolate croissant and a rock disguised as a chocolate croissant. Mass is the amount of stuff, matter, in an object. It's a measure of inertia, of how much that object resists being moved or sped up or slowed down. Weight, on the other hand, is the force exerted on that mass by gravity. One is the amount of you, the other is how hard the Earth is tugging at you. If you took a bathroom scale to the moon, for instance, your mass wouldn't change at all. You'd still be made of the same atoms, the same slightly mysterious arrangement of particles, but your weight, that would be significantly less because the moon's gravity is only about 1/6 that of Earth. So you'd step onto the scale and be pleasantly surprised, until you remembered that your pants still fit the same and your snacks are still gone. This distinction between mass and weight is not just academic, it's practical. Engineers have to consider mass when designing spacecraft because it affects momentum and fuel requirements. Astronauts might be floating around in microgravity, but their mass still resists motion, making even small movements a slow and clumsy ballet. Try pushing off a wall when your body doesn't want to stop, and you'll understand mass in a whole new, slightly embarrassing way. Even here on Earth, mass shows up in ways you may not consciously notice. Walking is a conversation with your own mass. Every step forward requires a transfer of momentum. Your foot pushes down and back, your body lurches forward, your center of mass shifts. This is why toddlers wobble so much. They haven't yet figured out how to coordinate their mass with the world beneath them, and why older adults, often with reduced muscle mass, are more cautious in their steps. Balance is really just an ongoing negotiation between mass and motion. Let's also talk about gravity's role in our daily relationship with mass. When you pick something up, your backpack, a pet, a child covered in peanut butter, you're not just lifting its mass, you're working against the gravitational pull of the Earth. The force you exert upward must be equal to the object's weight, which is mass times gravitational acceleration. That's why a feather and a brick have such different hefts, even though both fall at the same rate in a vacuum. Gravity doesn't play favourites, but it does multiply its effects by how much stuff it has to pull on. Interestingly, we don't often feel our own mass unless it becomes inconvenient. You might notice it when you try to run up a hill, or when your legs argue about standing after sitting too long. But it's not until we confront acceleration, starting, stopping, turning, that mass suddenly makes its stubborn presence known. Try catching a heavy box that slides off a shelf, and you'll feel the raw, unfiltered reality of mass in motion. This brings us to inertia, a concept tied tightly to mass. The greater an object's mass, the more it resists changes to its state of motion. That's why a truck takes longer to stop than a bicycle, and why pushing a refrigerator across the kitchen floor makes you question your life choices. Inertia is mass saying, "I'd rather not, thanks." Mass is also what gives momentum its oomph. Momentum is mass multiplied by velocity. A slow-moving bowling ball has more momentum than a speedy ping-pong ball. If you've ever stood in the path of either, you know this instinctively. And when it comes to collisions, whether it's bumper cars or two soccer players going head-to-head, it's the mass behind the motion that determines who gets pushed back farther. Despite how often we deal with mass, we rarely stop to ask what it is. It's tempting to say it's just stuff, but that explanation collapses the moment you look a little closer. Atoms are mostly empty space. The nucleus is a dense core, and even that is made of particles held together by invisible forces, and yet somehow, when you combine enough of those invisible bits, they add up to something that dents your car or tips your coffee mug. There's a curious elegance in how mass anchors us. It keeps our feet on the ground, literally and figuratively. Without mass, there'd be no resistance, no weight, no friction, and very little fun. You wouldn't be able to throw a ball, or sit comfortably in a chair, or even exist in the way you do now. You'd be a cloud of particles floating aimlessly through the void, like glitter spilled in space, dazzling, but disconcertingly useless. Think, too, about how we measure mass. It's not always with scales. Scientists use balances, accelerometers, and even orbital mechanics to infer mass. We've weighed planets by watching how their moons move, and estimated the mass of stars by how they wobble due to unseen companions. Mass doesn't need to introduce itself. Its effects make it impossible to ignore. There's also a beauty in how universally mass behaves. Whether you're on a mountaintop in Peru or floating in low Earth orbit, mass stays constant. It doesn't evaporate, it doesn't go bad, and it doesn't depend on your mood. It's one of the few physical properties that stubbornly refuses to be situational. Even your location in the universe can't shake it. In many ways, mass is the quiet backbone of reality. It shapes our world, not through loud declarations, but through consistency. It's in the resistance you feel when you swing a door open, the way your car hugs the road, and the firmness of the ground beneath your feet. It may be invisible, but it's never absent. Understanding mass isn't just about physics. It's about tuning in to the subtle forces that shape our lives. It reminds us that the world we move through is built from interactions both grand and microscopic, and that even the simplest experiences, like lifting a cup of tea, are rooted in deep, elegant principles. Mass might be quiet, but it speaks volumes. Once upon a time, in a sleepy English garden, a man named Isaac Newton watched an apple fall from a tree and began pondering one of the universe's most persistent questions. Why do things fall down? It's a charming story, often embellished, but behind that simple moment lies a revolution in thought that reshaped our understanding of motion, force, and of course, mass. Newton didn't just think about apples. He thought deeply about why objects move the way they do, or don't. His reflections led to 3 deceptively simple laws that form the backbone of classical mechanics and quietly govern nearly everything you experience in everyday life. Whether you're tossing a tennis ball, braking your car, or just standing perfectly still, Newton's insights are quietly whispering in the background. Let's begin with his first law, often called the law of inertia. An object at rest stays at rest, and an object in motion stays in motion, unless acted upon by a net external force. It's a beautiful, calming thought. Objects are lazy, really. They like whatever state they're in. If you give a hockey puck a push on a perfectly smooth surface, it will just keep going in a straight line forever and ever, unless something stops it. In reality, things like air resistance and friction get in the way, but the principle holds. Mass, in this context, is the measure of how stubborn an object is about changing its current motion. This brings us to the idea of inertial mass. Inertial mass is the kind of mass that resists acceleration. The more of it you have, the more force you need to speed up or slow down. That's why it's easier to push an empty shopping cart than one loaded with watermelons and inexplicably heavy detergent bottles. The mass is the same kind of thing in both carts. It's just that one has more of it. And as Newton's second law tells us, force equals mass times acceleration. Rearranged, this means acceleration equals force divided by mass. Bigger mass, smaller acceleration, unless you're a superhero. This simple equation, often written as F equals m times a, isn't just a tool for solving homework problems, it's a map of cause and effect. Apply a force and you'll get a change in motion. But how much that motion changes depends entirely on mass. A bowling ball and a balloon might both get the same push, but only one of them is going to move across the room like it means it. Now, Newton's third law is often the most quoted and possibly the most misunderstood. For every action, there is an equal and opposite reaction. This doesn't mean that bad decisions come back to haunt you, although they sometimes do. It means that if you push on a wall, the wall pushes back on you with the same force. If you jump off a boat, the boat gently drifts in the other direction. If a rocket blasts hot gas downward, the rocket moves upward. Equal and opposite. It's a cosmic dance, where every partner tugs on the other. Together, these three laws gave the world a powerful framework. For the first time, people could describe motion using math, predict trajectories, and understand why planets move the way they do. Newton's laws extended from apples to moons, from cannonballs to comets. He didn't just watch things fall, he watched the heavens, and he saw that the same rules applied everywhere. But Newton wasn't content with motion alone. He also wanted to understand gravity. What was this strange force that pulled apples down and kept the moon circling the Earth? In his law of universal gravitation, Newton proposed that every mass attracts every other mass with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. In other words, the more mass something has, the harder it pulls, and the farther apart two things are, the weaker the pull becomes. This gravitational attraction is where a second kind of mass comes into play, gravitational mass. It's the kind of mass that determines how strongly something feels gravity, and how strongly it pulls on other things. Strangely enough, when you measure an object's resistance to acceleration, its inertial mass, and its gravitational interaction, you get the same number. It's like the universe lined up two completely different jobs and hired the same candidate for both. This equivalence between inertial mass and gravitational mass is one of those peculiar features of physics that just works, though no one entirely knows why. In fact, centuries after Newton, it would become the basis of Einstein's theory of general relativity. But for now, what matters is that the two masses behave identically in every experiment we've ever performed. Imagine two very different objects, a bowling ball and a feather, falling in a vacuum. With no air resistance, they'll fall at the exact same rate. Their gravitational mass determines how much the Earth pulls on them, and their inertial mass determines how much they resist that pull. Because those two quantities are the same, they accelerate equally. That's not just physics, that's poetry with equations. Newton's ability to capture all of this in a few elegant laws changed everything. His framework didn't just predict planetary orbits, it gave us the tools to build bridges, design machines, and send probes to other worlds. It gave a name and a number to the quiet strength behind every motion: mass. One of the things that makes Newton's contribution so enduring is how intuitive it all feels. Even if you've never cracked open a physics textbook, you've lived these laws every day. You feel inertia when your car suddenly stops and you lurch forward. You feel action and reaction when you paddle a kayak or toss a basketball. And though gravity might seem like just a downward pull, Newton showed it's the gentle tug between all things, big and small. But for all its brilliance, Newton's view of mass was fundamentally mechanical. It was a measure of resistance, a source of gravitational attraction, a value plugged into neat equations that described how things move. It didn't ask why mass exists or what it's made of. It simply assumed mass was an inherent property of matter, there, unquestioned, like the firmness of the ground or the chill of a stone. This assumption worked beautifully for centuries. Newtonian mechanics predicted eclipses, powered steam engines, and guided cannonballs with eerie accuracy. In a world of moderate speeds and everyday scales, Newton's laws still hold strong. When you toss your keys onto the table or watch a pendulum swing, you're seeing classical physics in action. Newton gave us a universe that was reliable, calculable, and wonderfully predictable. And yet, even in this tidy, clockwork cosmos, there were hints that mass was more than it appeared. The fact that gravitational and inertial mass were always equal seemed suspiciously perfect, and the nature of gravity, how it acted instantly across vast distances, left questions lingering in the margins. Still, Newton's framework remains one of the greatest achievements in the history of science. His insights transformed mass from an everyday experience into a measurable, predictive, and universal quantity. He showed us that the forces we feel, the motions we observe, and the gravity we live with all stem from one consistent, elegant set of rules. It's easy to forget in the age of digital everything just how monumental this was. Newton took the chaos of motion and gave it order. He made the physical world understandable in a way it had never been before. And at the heart of it all was mass, not just as a measure of stuff, but as a quiet key to understanding the motion of everything. Imagine you're lying comfortably on the couch, completely at peace, swaddled in your favorite blanket with just the right amount of snack crumbs nearby. You know you should get up. Maybe the remote is just out of reach. Maybe your phone buzzed with something almost certainly unimportant, but you just don't move. That quiet, comforting refusal to be disturbed, that's inertia in its purest, laziest, most relatable form. Inertia is one of those ideas that you don't need a physics degree to understand. You feel it every day, even if you've never named it. It's the way your coffee tries to slosh when you accelerate the car, or why your laundry basket requires a dramatic grunt when you first pick it up. It's the resistance objects have to changes in motion, whether that means getting started, speeding up, slowing down, or changing direction. It's nature's way of saying, let's not be hasty. This resistance is not just an abstract concept, it's tied directly to a property called inertial mass. Inertial mass is how much something resists being accelerated. If you apply a certain amount of force to two different objects, and one accelerates more than the other, the one that resists more has more inertial mass. It doesn't matter whether you're pushing a box across a floor or shoving a shopping cart down an aisle, you're feeling its inertia every time you apply force and wait for the object to reluctantly respond. There's something almost poetic about how this plays out in daily life. Picture a boulder and a beach ball sitting side by side. Give each a gentle push. The beach ball rolls off like it's been waiting for an excuse, light and eager. The boulder doesn't even flinch. It knows its worth. It needs persuasion. It has more mass and therefore more inertia. Even when you're just trying to start walking after sitting still for a while, your own body's inertia is part of the experience. Muscles stretch, joints creak, and you feel like you're shaking off invisible glue. That initial effort is your body working against its own inertia. Once you're moving, things get easier, momentum takes over, but it's that start that always feels like the heavier step. Now here's something quietly wonderful about inertial mass. It doesn't care what something's made of. A bag of feathers and a bag of sand, if they weigh the same, resist motion the same way. The contents might behave differently once they get going, feathers float and sand flops. But in terms of getting started, it's the mass that counts, not the material. Inertia doesn't play favorites. This is one of the things that makes inertial mass so clean and elegant. It's not about stickiness or friction or how awkwardly shaped something is. It's about how much force it takes to change the object's velocity. Imagine a perfectly smooth hockey puck on a perfectly smooth sheet of ice. Give it a push, and it glides on serenely. That glide, uninterrupted, is inertia in motion, literally. Of course, we don't live in a frictionless world. Everything has some kind of resistance, air, surfaces, textures. But if you remove those distractions, inertia reveals itself as the underlying principle. It's what allows the laws of motion to make sense. Force leads to acceleration, yes, but only if the object is willing to budge, and its willingness? That's all down to inertial mass. Now, how do we actually measure inertial mass? It's surprisingly straightforward. You apply a known force and observe the acceleration. For example, if you have a spring that always pushes with the same strength, and you attach it to different objects and see how quickly they accelerate, you can compare their inertial masses. The object that accelerates less must have more mass, because it's more resistant to being moved. This principle is so dependable, we've been using it to weigh and compare objects for centuries. In laboratory settings, scientists use devices like inertial balances, essentially spring-based systems that measure how long it takes an object to oscillate back and forth. The longer the period, the more mass the object has. No gravity required, no fancy equipment, just the raw, rhythmic tug-of-war between inertia and the restoring force of a spring. It's a beautiful demonstration of how mass can be sensed without even needing weight. One of the more delightful ways to think about inertia is to imagine mass as personality. Some objects are just stubborn. A heavy crate doesn't want to go anywhere unless you beg it with your entire body. A small ball practically flings itself out of your hand. It's like some things are set in their ways, while others are more free-spirited. In physics terms, the more mass something has, the harder it is to persuade it to do anything new. You can also see inertia playing out in transportation. Think about how long it takes a massive train to get up to speed. Engineers have to apply force gradually, building momentum over time, and once the train is moving, it doesn't stop easily. Its huge mass resists both starting and stopping. It coasts forever. That's inertia, with steel and steam. Even the simple act of turning a car involves inertia. Your body wants to keep going in a straight line, even as the vehicle changes direction. That's why you feel pulled to the side during sharp turns. Your body isn't actually being pushed sideways. It's just trying to keep moving straight, and the car is insisting otherwise. In sports, inertia becomes a silent player. A football flying through the air stays on its path until wind, gravity, or a pair of hands says otherwise. A sprinter bursting from the starting blocks has to overcome their own inertia in those first milliseconds. Even juggling, oddly enough, involves constant negotiation with the inertia of each ball, keeping them in the right rhythm, never letting them settle, and there's something wonderfully grounding in knowing that inertia is universal. From the tiniest dust mote to the largest asteroid, all things resist changes to their motion. The same principle that applies to a marble rolling across a kitchen floor also governs the movement of planets and stars. Inertia scales up and down, never breaking, never changing. It's a quiet, persistent force of order in a dynamic world. In your own body, every step, every stretch, every sleepy shift under the blanket at night is a dialogue with inertia. It's the reason you can feel motion, the reason your morning coffee doesn't leap from the cup when you stop too quickly, and the reason you brace yourself before moving something heavy. It's not just an abstract scientific term, it's part of the way you interact with reality constantly. Even our technology relies on understanding inertia. Accelerometers, used in smartphones and spacecraft alike, work by detecting the resistance of small masses to movement. They allow your phone to know when you've turned it sideways, and they help satellites navigate by reading tiny shifts in momentum. Inertial guidance systems depend entirely on the principle that mass resists acceleration, giving us precision in a world of movement. At its core, inertia is about stability. It's the universe's way of saying that things don't change unless something makes them, and that idea, that resistance to change, is deeply comforting. It means the world isn't entirely chaotic. Objects have memory in a sense. They keep doing what they were doing until nudged by a force. That quiet persistence is one of the reasons we can predict motion, build structures and catch a ball without it behaving randomly. Inertial mass isn't loud or dramatic. It doesn't sparkle or glow. It just is, always resisting, always steady, always ready to make your lazy evening on the couch just a little more justified. After all, getting up would require force, and inertia, as always, prefers you stay right where you are. Gravity has a way of making itself known. It's the reason your socks stay on the floor instead of floating off to form a cozy halo around your ceiling light. It's why your morning toast lands butter side down with the confidence of a gymnast sticking a dismount. Gravity, in all its silent strength, is the invisible tether holding us to the Earth, keeping the moon in orbit and guiding the dance of galaxies across the cosmos. And as it turns out, it's also one of the best ways we have of measuring mass, even the kind we'll never see or touch. It all starts with a pull. Every object with mass attracts every other object with mass. That includes you, your neighbour's cat, and the distant rings of Saturn. The strength of that gravitational attraction depends on two things: the masses involved and the distance between them. The bigger the mass, the stronger the pull. The farther apart the objects, the weaker the connection. This relationship is described by Newton's law of universal gravitation, a lovely bit of mathematics that says the force of gravity is proportional to the product of the two masses, divided by the square of the distance between them. Now, this might sound like something best left on a chalkboard, but you can feel it every day. When you drop a pencil, Earth's mass is pulling it downward. Your body presses into your mattress at night because of that same gravitational hug. You don't think about it often, but you're in a constant embrace with the planet, always being pulled gently downward. Gravity also gives us a remarkably handy way to detect mass, even when we can't see the mass directly. That's how we know how much the Earth weighs, or more precisely how much mass it has. You can't pop the Earth onto a giant scale, but you can observe how it interacts gravitationally with other objects like satellites. By studying their orbits, you can calculate the gravitational force acting on them, and from that, determine the mass of the body doing the pulling. It's a bit like watching how tightly a tetherball swings around its pole, and using that information to figure out how heavy the pole is, all without ever touching it. One of the most famous examples of this kind of gravitational detective work was done by Henry Cavendish in the late 18th century. He didn't actually set out to weigh the Earth. That was a bonus. What he built was a device called a torsion balance, a delicate setup with lead spheres hanging from wires that twisted ever so slightly due to the gravitational attraction between the spheres. By measuring the angle of the twist, Cavendish could calculate the strength of the gravitational force, and from that deduce the mass of the Earth. All from a wooden shed, using tiny movements and painstaking patience. Not bad for a man in breeches. Gravity scales beautifully from the tiny to the titanic. You can feel it in your knees as you walk upstairs, and astronomers can see it bending light as it travels past entire clusters of galaxies. That bending of light, known as gravitational lensing, reveals the presence of mass that would otherwise be invisible, like a fingerprint left by an unseen hand. When light curves around something in space, we know it's not the light misbehaving, it's gravity, doing its job. This same gravitational influence is also responsible for the tides. The moon's mass pulls on the oceans, gently tugging the water into bulges that shift as the Earth rotates. The result? High tide and low tide, a soothing rhythm that has guided sailors, poets, and beachcombers for centuries. What's fascinating is that both the Earth and the moon are pulling on each other. The moon raises tides on the Earth, and the Earth raises tides on the moon. That's gravity style, mutual, unceasing, and very democratic. No object escapes its influence, no matter how large or small. Even distant planets can reveal their mass through gravitational interactions. When astronomers observe the motion of moons around Jupiter or Saturn, they can calculate how much mass those planets must have to keep their moons in orbit. The same trick works for exoplanets, which are far too faint to see directly. By watching how a star wobbles ever so slightly under the gravitational pull of an orbiting planet, we can deduce the planet's presence, its orbit, and even its mass. It's like hearing the faint creak of floorboards and knowing someone is tiptoeing nearby. Gravity is also what helps us estimate the mass of entire galaxies. When we look at stars orbiting the center of a galaxy, their speed should drop off the farther out they are, like cars on the edge of a roundabout. But they don't. They keep moving at high speeds, as if there's more mass holding them in place than we can see. That unseen mass is what we call dark matter, a mysterious something that reveals its presence only through gravity. It doesn't glow, it doesn't reflect, it doesn't chat at parties. But it's there, holding galaxies together. What's especially intriguing is that gravity always tells the truth. It doesn't care whether you can see the mass or not. If there's a gravitational effect, there's mass behind it. You can't fake it. You can't Photoshop it. That honesty makes gravity a kind of cosmic scale, one that lets us weigh the invisible and explore the unknown. Even black holes, those dense, light-swallowing beasts of the universe, announce their mass through gravity. We can't see the black hole itself, but we can watch stars orbiting an empty spot and know exactly what kind of heavyweight is lurking there. In fact, some of the best evidence for black holes comes from observing the orbits of nearby stars, tracking their curved paths and inferring the mass required to keep them in those trajectories. It's tempting to think of gravity as a force that just pulls things down. But in reality, gravity is the architect of structure. It shapes planets, holds atmospheres, forms galaxies, and binds the universe together in a quiet but relentless way. Without it, the universe would be a cloud of particles floating alone in the dark. With it, we get stars, orbits, tides, and the soothing tug of a hammock on a summer day. The scales of gravity stretch far beyond our daily lives, but they start with the same principles. Drop a spoon, and you're participating in the same force that shapes galaxies. Sit down on a chair, and you're pressing your mass into the earth while the earth presses right back. It's all part of a grand exchange, mass communicating silently across space. Even the earth itself is not immune to the influence of distant masses. The sun's gravity keeps us in orbit, while Jupiter's gravitational field subtly tugs on the entire solar system. Nothing floats entirely free. Every motion is part of a wider network of gravitational whispers, a delicate interplay that spans from the atomic scale to the cosmic. And through all this, mass is both the instigator and the listener. It responds to gravity and causes gravity, resists motion and invites measurement. It's mass that allows gravity to do its quiet work, revealing itself not in a loud announcement, but in the sway of the tides, the arc of the moon, and the fall of a leaf. There's a gentle harmony to it all, a cosmic choreography set to a rhythm we've only just begun to understand. Gravity isn't just a force, it's a language, and mass, in all its stillness, is how that language is spoken. Let's take a moment to appreciate just how strange and wonderful the universe really is. You're sitting there, comfortably still, not moving a muscle, and yet, inside you, trillions of atoms are buzzing with energy. And here's the twist. All that buzzing isn't just a side effect of being alive, it's part of what gives you mass, not just metaphorically, literally. According to Einstein, your mass is your energy, and not just a little energy, but an absolutely enormous amount. In fact, even the tiniest bit of mass contains enough energy to power entire cities. It just doesn't usually want to give it up. This mind-bending idea is tucked neatly into one of the most famous equations in all of science, E equals mc squared. It's short, elegant, and often printed on coffee mugs and t-shirts. But behind its simplicity lies a world-shaking truth. Energy and mass are two sides of the same cosmic coin. They're interchangeable. If you have one, you can get the other. Let's unpack this in plain terms. The E stands for energy, the M is mass, and C is the speed of light in a vacuum, an enormous number, roughly 300 million meters per second. When you square that speed, you get an even more enormous number. That means even a small amount of mass multiplied by that colossal factor gives you a truly staggering quantity of energy. This isn't just theoretical. The equation has real consequences. It explains why nuclear reactions are so powerful. In both fission and fusion, a tiny bit of mass vanishes, and in its place, a burst of energy is released. The sun shines because hydrogen atoms fuse together to form helium, and in the process, a tiny fraction of their mass gets converted into light and heat. It's a nuclear transaction, a little mass traded for a lot of warmth. The idea that mass is concentrated energy also means that energy in turn has mass. Not in the same stand on a scale kind of way, but in a real, measurable sense. If you add energy to a system, say by heating it up, it actually becomes more massive. Very slightly, of course. You're not going to gain weight from drinking hot tea instead of iced. But the physics is there, humming away in the background. Heat, light, kinetic energy. They all contribute ever so gently to mass. In particle accelerators, this becomes beautifully clear. Smash particles together at high speeds, and the energy from the collision can create entirely new particles. It's like magic, except governed by the firm rules of quantum field theory. The energy didn't vanish, it transformed into mass. The resulting particles have weight, charge, and personality, all born from pure high-speed energy. In a very real sense, mass is what happens when energy settles down, when it stops racing around at light speed and agrees to take up space, resist motion, and be weighed. It's energy that has made a long-term commitment. Mass is like the calm after a wild night of energy bouncing around the universe. It's the moment when energy decides to stay in one place, at least for a while. And this has implications far beyond the lab. It tells us something profound about the nature of everything. You, me, these stars, the air. We're all made of energy, frozen into a slower, heavier form. When you walk through the world, your mass isn't just some arbitrary number. It's a reflection of your energy content, as surely as your temperature reflects your heat. Einstein's insight didn't come from a lab bench or a telescope. It came from playing with equations and thinking deeply about how light and motion work. He realized that as an object gains energy, it also gains inertia. And if it gains inertia, that's the same as gaining mass. The more energy it has, the harder it is to change its motion. It doesn't matter whether the energy is stored chemically, thermally, or electromagnetically, it still contributes. This idea also unifies the forces of nature in a surprising way. If mass and energy are equivalent, then gravity doesn't just act on mass, it acts on energy too. A beam of light, even though it's massless in the traditional sense, still bends around massive objects because it has energy. It's this very principle that led Einstein to develop his theory of general relativity, where gravity is not just a force, but the curvature of space-time itself caused by energy and mass. You might wonder then why everything isn't constantly exploding, shedding its mass and bursting into energy. After all, if there's that much energy stored in matter, shouldn't we all be little ticking stars? Fortunately, converting mass into energy requires very specific conditions. You can't just squeeze a chair and expect it to emit a warm glow. It takes processes like nuclear fusion, matter-antimatter annihilation, or extreme gravitational fields to unlock that transformation. Speaking of annihilation, when a particle meets its exact antiparticle, say an electron and a positron, they annihilate completely, leaving behind only energy. No scraps, no leftovers, just a flash of photons. All of their mass becomes pure electromagnetic radiation. It's one of the cleanest demonstrations of E=mc² in action. This elegant relationship also gives us insight into the structure of atoms. The mass of an atom isn't just the sum of its parts. When protons and neutrons bind together in a nucleus, the total mass is actually a little less than the sum of the individual particles. That missing mass, the mass defect, has been released as energy when the nucleus formed. The atom is holding itself together tightly, and that binding energy has left its mark by slightly reducing the mass. Again, mass and energy, swapping places in a quiet transaction. Even black holes obey this rule. As matter falls into a black hole, it heats up and releases energy, sometimes in jets that scream out across space. The remaining mass contributes to the gravity of the black hole itself. Some of the original mass is now light, some is kinetic energy, and some becomes part of the black hole's insatiable appetite. All of it governed by the same elegant equation. There's something deeply satisfying about the idea that mass and energy are not separate things, but different expressions of the same underlying reality. It adds a kind of unity to the universe, as if nature is whispering, everything is made of the same stuff, it just wears different clothes. Energy can dance as light, surge as electricity, or curl up quietly as mass. It all depends on the context. Even time is part of the story. A clock on a moving spaceship ticks more slowly, not just because of its speed, but because its energy affects how time flows around it. And energy, remember, means mass. The greater the energy, the stronger the gravitational field it produces and the more space-time curves. Everything is connected, woven together through this intimate dance of motion, mass, and time. Einstein's little equation is more than a physics fact. It's a statement about the nature of reality itself. It tells us that nothing is ever truly static, that even the stillest object is brimming with hidden energy, and that, given the right conditions, that energy can move, shine, transform, and reshape the universe. So the next time you pick up a rock, or stir your tea, or look up at the glowing disk of the sun, you're interacting with energy in one of its most loyal forms, mass. It may seem solid and slow, but at its core it's pure potential, quietly waiting, coiled within every atom. Mass, it turns out, is not just weight. It's the energy of the universe, at rest. At first glance, atoms don't seem like they should carry much weight. After all, they're incredibly small, so small that millions of them could line up across the width of a single human hair and still leave space for a coffee break. They're the tiniest building blocks of matter, the miniature scaffolding of everything you see and touch. And yet, for something so small, atoms pack a surprisingly dense punch. Their mass is real, measurable, and full of mystery. Now, when you hear atomic mass, it's tempting to imagine that we're just tallying up the weight of all the bits inside, protons, neutrons, electrons, and calling it a day. But nature, as always, refuses to be that straightforward. In fact, atomic mass isn't just the sum of the particles inside. There's more going on, hidden contributions, missing pieces, and invisible forces that hold everything together and, paradoxically, make the whole weigh less than the sum of its parts. Let's start with the basics. Every atom is made up of three kinds of particles: protons and neutrons in the nucleus, and electrons buzzing around them like a cloud of overexcited fireflies. Electrons are important, of course. They handle chemistry, electricity, and making your hair stick up when you touch the wrong doorknob. But in terms of mass, they barely show up. Each electron has about 1/2000th the mass of a proton. If an atom were a sandwich, the electrons would be the sesame seeds on the bun. So where does the mass come from? Mainly the nucleus, that dense central core where the protons and neutrons reside. These particles, known collectively as nucleons, make up more than 99.9% of the atom's mass. And they are heavy not because they're particularly large, but because of the energy locked inside them. Remember Einstein's equation? Mass is energy, and these particles are practically humming with it. But here's where things get interesting. If you were to add up the mass of the individual protons and neutrons in a nucleus, separately, as if they were floating in space, you'd end up with a number that's slightly more than the actual mass of the nucleus when it's bound together. That difference, that missing bit of mass, is called the mass defect. It hasn't vanished. It's been converted into binding energy, the glue that holds the nucleus together. This binding energy is no small matter. It's what keeps the positively charged protons from flying apart in a burst of electromagnetic rebellion. Remember, like charges repel, and protons are all positively charged. In a tiny space like a nucleus, they should be repelling each other with enough force to make a toaster blush. But they don't, because of the strong nuclear force, a powerful but short-range interaction that acts like an atomic bouncer, keeping everything in line. The strong force is one of the four fundamental forces of nature, and it's aptly named. It's the most powerful of them all, but it only works over incredibly small distances, about the size of a nucleus. When protons and neutrons get close enough, the strong force overwhelms the repulsion between protons and binds them together. The result is a stable nucleus, with a bit of its mass having been sacrificed to create the binding energy that holds it all in place. This mass defect is why nuclear reactions release so much energy. When a nucleus splits apart, or when small nuclei fuse together, the change in binding energy appears as released energy, sometimes in the form of light, heat, or radiation. It's why the sun shines, and why nuclear power plants hum with controlled intensity. The tiny difference between what was and what is becomes a vast reservoir of usable energy. Different atoms have different amounts of binding energy per nucleon, and this affects their overall mass. Iron, for example, sits near the top of the binding energy curve. It's incredibly stable, which means it's difficult to squeeze more energy out of it through fusion or fission. That's why stars eventually run out of steam when they start making iron. It's nature's atomic dead end. No more energy to gain, no more fusion to fuel the fire. As we take a stroll through the periodic table, the trend becomes clear. Heavier atoms have more nucleons and thus more mass, but not in a simple one-to-one fashion. For instance, uranium has 92 protons and around 146 neutrons. That's a lot of mass, but the total isn't just 92 times the mass of a proton plus 146 times the mass of a neutron. The binding energy and internal structure mean the real number is a little less, a reminder that mass is not simply a tally of ingredients, but a reflection of how those ingredients are arranged and held together. Even within the same element, different atoms can have slightly different masses. These are isotopes, atoms with the same number of protons but varying numbers of neutrons. Carbon, for example, usually comes in the form of carbon-12, with 6 protons and 6 neutrons. But there's also carbon-13 and carbon-14, each with more neutrons and slightly more mass. These variations give rise to all kinds of interesting behaviors, from radioactive decay to radiocarbon dating, which lets us peek into the age of ancient bones and forgotten campfires. In fact, the average atomic mass you see listed for each element on the periodic table isn't a single number at all. It's a weighted average of all the stable isotopes of that element, based on their natural abundance. So when you see that chlorine has an atomic mass of about 35.5, it's because nature serves it up as a blend, roughly 75% chlorine-35 and 25% chlorine-37, a little bit of statistical flair in an otherwise stoic column of numbers. Zooming in even further, we find that protons and neutrons themselves aren't fundamental. They're made of smaller particles called quarks, held together by even more energetic glue, the aptly named gluons. Most of the mass of a proton or neutron doesn't come from the mass of the quarks themselves, which are tiny even by particle standards, but from the energy of the gluons binding them. It's like a dance floor where the dancers weigh almost nothing, but the spinning and twirling of the choreography makes the whole place shake. In this way, atomic mass becomes something deeply holistic. It's not just about the number of particles, it's about how those particles are arranged, how tightly they cling to one another, and how much energy is coursing through their relationships. It's a mass made from motion, from binding, from potential. Even when atoms come together to form molecules, tiny changes in mass can occur. When two atoms bond, they release a small amount of energy, which slightly reduces the mass of the resulting molecule. Again, it's a negligible amount, but it's real. Chemistry, it turns out, is also a game of energetic trade-offs, and mass tags along for the ride. So while the atom may be small, its mass is anything but simple. It's not just the sum of parts, but a reflection of how those parts interact. It's the story of particles in motion, of forces at play, of energy making itself at home. Atomic mass is a kind of quiet bookkeeping by the universe, tracking the balance between stability and potential, between what is and what could be released. And that makes it more than just a number on a chart. It's a window into the heart of matter itself, a peek into the invisible scaffolding of reality, all packed into a space so tiny you could fit trillions into a single grain of sand. Heavy indeed, for something you'll never see. Imagine you're sitting comfortably on a train that's gliding along perfectly smooth tracks, sipping a hot drink and gazing out the window as the landscape rolls by. Now imagine another train zooms past in the opposite direction, and someone on that train is also enjoying a quiet beverage. From your perspective, they're flying by. From their perspective, you are. But here's the weird part. Both of you are right. Welcome to special relativity, where motion is relative, time can stretch, and even mass seems to play tricks if you're not careful about how you define it. One of the most common myths in popular science is that mass increases as you approach the speed of light. It's a juicy idea. You picture a spaceship hurtling faster and faster, growing heavier and heavier, like some kind of cosmic carb loading. But it's not quite true, not in the way we understand mass today. What actually increases isn't mass, but energy, and that distinction makes all the difference in the universe. To make sense of this, we have to introduce two different flavors of mass. The first is rest mass, also called invariant mass. It's the mass an object has when it's not moving relative to you. This is the kind of mass that shows up in Einstein's famous equation, the kind you'd assign to a particle on its birth certificate. It doesn't change, no matter how fast the object moves. A proton at rest and a proton zooming through space both have the same rest mass. The other kind, often called relativistic mass, was more commonly used in the early days of relativity, but physicists today tend to avoid it because it can create confusion. Relativistic mass is essentially the energy of an object, divided by the speed of light squared. As an object's speed increases, so does its energy, and if you're using the older definition, that increase in energy appears as an increase in mass. But calling it mass muddies the waters. What's really changing is the object's total energy, and with it, how hard it is to accelerate. Think of it this way. The faster something moves, the more effort it takes to make it go even faster. At everyday speeds, this effect is so tiny that we never notice it. But as you get closer to the speed of light, that resistance skyrockets. You can pour more and more energy into the system, and instead of speeding up like it used to, the object starts hoarding that energy as increased inertia. It feels heavier, not because its mass has increased, but because you're dealing with the strange rules of energy and motion at high speeds. This is one of the key insights of Einstein's theory of special relativity, published in the early 20th century. It showed that space and time aren't separate things. They're intertwined, forming what we now call space-time. As you move faster, your experience of time slows down and distances appear to contract. From your point of view, everything seems normal. But to an outside observer, you're taking your sweet time moving through a compressed version of space. This brings us back to our trains. Imagine a beam of light traveling through the cabin of a moving train, bouncing between the floor and the ceiling. To someone inside the train, the beam moves straight up and down. But to someone standing outside watching the train speed past, the light traces a longer diagonal path because the train has moved during the light's journey. Since the speed of light must remain constant for all observers, one of the bedrock principles of relativity, the only way to reconcile this is for time to slow down on the moving train. And it does. This time dilation is not just a mathematical curiosity. It's been observed again and again. GPS satellites, which orbit high above the Earth at high speeds, have to account for both special relativity and general relativity when keeping time. Without those corrections, your navigation system would be off by several kilometers in just a day. Relativity might sound exotic, but it's quietly guiding your phone through traffic right now. Now, let's think bigger. High-energy particle accelerators, like the Large Hadron Collider, accelerate protons to speeds approaching the speed of light. These particles gain incredible amounts of energy, but their rest mass remains the same. What changes is how much energy they carry, and how that energy affects their motion, collisions, and interactions. In these extreme realms, energy dominates the conversation, and mass becomes just one part of the equation. Cosmic rays, high-energy particles from space, often slam into Earth's atmosphere at speeds so close to light that their behavior becomes downright peculiar. They can create particle showers, alter atoms, and travel distances that, from their perspective, take far less time than they do for us. Their clocks are ticking slower, their paths are compressed, and yet they're just particles, obeying the same laws as everything else. There's something deeply elegant about how all of this ties together. When you see an object moving, what you're really seeing is energy in motion. That energy affects how the object behaves, how it interacts, how it resists acceleration, how it warps space-time. You're not watching mass change, you're watching energy shape reality. This distinction also helps preserve the beauty of conservation laws in physics. Rest mass is conserved in particle reactions. It remains the same before and after a collision, assuming no particles are created or destroyed. Total energy, which includes the energy of motion, is also conserved. when you stop thinking of mass as something that swells with speed and instead focus on energy, the puzzle pieces fit together more smoothly. Even photons, particles of light that have no rest mass, carry energy and momentum. They may not weigh anything in the traditional sense, but they can exert pressure, transfer energy, and be influenced by gravity. This shows us that mass is not the sole gatekeeper of physical influence. Energy is the true currency of the universe, and mass is simply one of the ways that energy chooses to manifest. Rest mass, then, becomes a kind of anchor point. It tells us how much energy an object has when it's just sitting still, doing nothing, watching the clouds roll by. Any additional energy, heat, motion, excitement, adds to the total energy, but not to the rest mass. The core identity remains the same. In many ways, this whole relativistic dance invites us to see mass not as a rigid number, but as a kind of energy signature. It's energy at rest, energy contained, energy expressing itself with patience. And when that energy begins to move, faster, nearly light speed, it doesn't grow heavier. It becomes more difficult to budge, more influential, more potent. But it's still the same essence, just playing by the intricate rules of space-time. So if you ever find yourself imagining a spaceship speeding through the cosmos, brushing up against the speed of light, don't picture it bulging with extra mass like it's been snacking along the way. Picture it shimmering with energy, wrapped in stretched time, carving its path through a universe where space and time bend and twist with motion. It hasn't gained weight, it's just fully committed to the journey. There's a strange kind of magic hiding in plain sight all around you, something invisible, silent, and everywhere. It's not gravity, although that's a good guess. It's something more peculiar, a field spread out through every inch of space, touching every particle that moves through it. This is the Higgs field, and according to our best understanding of physics, it is the reason why you, your teacup, and the moon all have mass. To wrap your mind around this idea, you'll need to leave behind the notion that space is just an empty backdrop. In modern physics, empty space is never truly empty. Instead, it's more like a restless canvas where invisible fields ripple and shimmer with potential. Each of the fundamental forces has its own associated field. The electromagnetic field gives rise to light. The gravitational field shapes the paths of planets. And the Higgs field, well, that's the one responsible for a very specific kind of mischief. It endows particles with mass. But how does that actually work? It helps to picture the Higgs field not as some spooky ghost wafting through the room, but more like a cosmic kind of molasses. Imagine you're a particle trying to move through a room filled with this molasses-like substance. Some particles glide through easily, barely slow down like a greased marble on glass. Others get bogged down, trudging forward as if wearing boots full of peanut butter. The more the particle interacts with the field, the more it feels the field's resistance, and the more mass it seems to have. Another way to picture it is the famous celebrity at a party metaphor. Imagine a crowded room, filled with people chatting and mingling. Now, picture a celebrity walking in. Suddenly, everyone gathers around them, asking for autographs and selfies. The celebrity moves more slowly because they're constantly interacting with the crowd. Meanwhile, a completely unknown person walks through the room unnoticed, gliding right through without resistance. In this version of the story, the room is the Higgs field. The crowd is how strongly the particle interacts with the field, and the resistance, that's mass. So mass, in this view, isn't just something a particle carries around like a backpack. It's a result of interaction. Particles moving through the Higgs field gain what looks and feels like mass, because the field slows them down. The more they interact, the heavier they become. The origin of this idea goes back to the 1960s, when several physicists, including Peter Higgs, were trying to solve a problem. The equations that described fundamental particles and forces worked beautifully, unless you tried to include mass. In those cases, the equations fell apart like a badly balanced soufflé. To fix it, physicists proposed a clever mechanism. What if mass wasn't a built-in property, but something particles acquire through interaction? introduce a new field permeating all of space, and allow particles to couple with it. Voila, mass emerges. It was an elegant solution. The field gives mass to the particles in the Standard Model, the framework that describes all known fundamental particles and their interactions, except gravity. Without the Higgs field, some particles would move at the speed of light and never settle down. Atoms wouldn't form, chemistry wouldn't exist. You wouldn't be sitting here listening to someone talk about molasses in space. For decades, this idea remained theoretical. The Higgs field made the math work, and it seemed to explain why some particles have mass while others, like photons, do not. But a field is hard to detect. What's easier to find is its associated particle. Just like the electromagnetic field gives rise to photons, the Higgs field should give rise to a Higgs boson. And so began one of the greatest scientific quests of the modern era. Finding the Higgs boson would not only confirm the existence of the field, it would complete the Standard Model. The challenge? You can't just scoop up a Higgs boson in a net. It's incredibly heavy by particle standards, unstable, and vanishes almost instantly after being created. To even have a chance at creating one, scientists needed to smash particles together at insanely high energies not found in nature since just after the Big Bang. Enter the Large Hadron Collider, a vast underground ring stretching over 25 kilometers beneath the border of France and Switzerland. Operated by CERN, the European Organization for Nuclear Research, it's the most powerful particle accelerator in the world. Think of it as a circular racetrack for protons, where they're pushed to nearly the speed of light, then crash together in tiny but spectacular head-on collisions. On July 4th, 2012, scientists at CERN announced something extraordinary. After years of data collection and analysis, they had found strong evidence of a new particle with a mass of about 125 giga-electron volts, just where the Higgs boson was expected to be. The discovery made headlines around the world. There was applause, champagne, and more than a few joyful tears in labs and lecture halls. Peter Higgs himself, then in his 80s, was present for the announcement. He reportedly wept. What made the discovery so emotional was not just that it confirmed a prediction. It validated an entire worldview. The idea that mass arises from interaction with a field wasn't just an abstract trick anymore, it was part of the fabric of the universe. We had touched the mechanism that gives weight to reality. The Higgs boson is a fleeting thing. It decays almost instantly into other particles, photons, W bosons, bottom quarks. These decay products are what physicists actually detect. The process is like finding footprints in the snow and deducing what kind of animal passed by, even if the animal itself is long gone. But those footprints were enough. They match the pattern predicted by the Higgs theory, with remarkable precision. It's important to note that the Higgs field doesn't explain all mass. Most of the mass in protons and neutrons doesn't come from the Higgs field at all. It comes from the energy of the strong nuclear force binding their constituent quarks together. But the Higgs field is what gives mass to the quarks themselves, as well as to particles like electrons and W and Z bosons. Without it, those particles would be massless and zipping around at light speed. The universe would be a very different place. All of this ties into a deeper framework known as quantum field theory. In this view, every fundamental particle is actually a ripple in a corresponding field. An electron is an excitation of the electron field. A photon is a ripple in the electromagnetic field. The Higgs boson is a blip in the Higgs field. The universe becomes a vast sea of invisible energy, filled with overlapping fields that interact, fluctuate, and occasionally bubble up into something tangible. It's a strange but beautiful picture. The vacuum is not empty, it's buzzing with potential. Fields stretch across space and time, shaping the behavior of particles and forces, and mass, that seemingly solid and intuitive property, is actually the result of moving through one of these invisible fields, like wind through tall grass. The discovery of the Higgs boson wasn't the end of the story. If anything, it opened the door to new mysteries. Why does the Higgs field have the strength it does? Could there be more Higgs-like particles? Is there a deeper layer beneath the Standard Model waiting to be uncovered? For now, though, we can marvel at the fact that our universe has a mechanism for giving things substance. That mass is not a primitive, unexplained trait, but a result of deeper interactions. It turns out that space itself plays a role in shaping what things are and how they move. And somewhere out there, every second of every day, particles are wading through the Higgs field, becoming something more than just points of energy. They're becoming real, weighted, tangible, thanks to a field that's always been there, quietly waiting to be discovered. Imagine a ballroom filled with particles, all dressed for the occasion. Some waltz gracefully across the floor, barely noticing the crowd. Others stumble, weighted down, tugging at invisible partners as they try to dance. In this curious subatomic soiree, mass is more than just a number. It's a defining feature that determines who can glide freely and who gets tangled up in the room's invisible currents. Let's start with the ones that move with absolute freedom. The photons. These are the life of the lightspeed party. Photons have no mass whatsoever, which allows them to travel at the cosmic speed limit, roughly 300 million meters per second, without breaking a sweat. That masslessness isn't just a bonus trait, it's essential. If photons had even the tiniest smidge of mass, light itself would behave very differently. It might slow down, change its energy spectrum, or even fizzle out over long distances. Thankfully, that's not how it works. Light, as far as we can tell, is completely massless, and that's what allows it to streak across space for billions of years, carrying messages from the edge of the observable universe to your eyes. Now contrast that with the W and Z bosons, the heavyweights of the particle dance floor. These particles mediate the weak nuclear force, which is responsible for processes like radioactive decay. They don't move with the breezy elegance of photons. Instead, they're massive, sluggish by particle standards, and short-lived. The W boson tips the scale at around 80 giga-electron volts, and the Z boson is even heavier, clocking in at about 91. That's nearly 100 times the mass of a proton. For particles, that's like showing up to a foot race in a full suit of armor. So why do these force-carrying particles have mass, while the photon doesn't? The answer lies in how they interact with the Higgs field. The photon doesn't couple to the Higgs field at all, which means it slips through space unimpeded. The W and Z bosons, however, are not so lucky. They couple strongly with the Higgs field and, as a result, gain mass. This difference is critical because it directly affects the behavior and range of the forces they carry. Massive force carriers, like the W and Z bosons, lead to short-range forces. The weak nuclear force, for instance, only acts over distances much smaller than the size of an atom. It's so short-range that you'd never notice it in daily life. The mass of the W and Z bosons is what makes the weak force weak. It limits their influence, keeps their effects confined to the quantum shadows. Meanwhile, the photon's lack of mass allows electromagnetism to reach across vast distances, from the glow of a star to the tip of your finger. This elegant contrast is part of why the standard model is so effective. It's not just a list of particles, it's a blueprint of how mass governs interaction. Force, reach, decay, behavior, all of it is shaped by whether or not a particle carries mass. And nowhere is this more curious than with the neutrinos. Ah, neutrinos, the wallflowers of the particle world. They're shy, barely interacting with anything, and yet they're everywhere. Trillions of them are passing through you right now, through your chair, through the floor. They come from the sun, from distant supernovae, from radioactive elements in the earth. And they do all of this without ever asking permission or leaving much of a trace. For a long time, physicists believed neutrinos were completely massless, like photons. It made sense. They hardly interacted with anything, and their behavior suggested they had no inertia to speak of. But then, something strange happened. Physicists observed a phenomenon known as neutrino oscillation, where one type of neutrino slowly transforms into another as it travels through space. This was a cosmic clue with big implications. In order for neutrinos to oscillate between flavors, electron, muon, and tau, they must have mass, tiny, elusive, feather-like mass. It's not much, and we still haven't pinned down exactly how much, But the fact that they have any mass at all shattered a long-standing assumption in physics. It also confirmed that the standard model, while powerful, isn't the whole story. Something deeper is at work. Neutrinos are unique in many ways. First, they only interact via the weak nuclear force and gravity, which means they don't bounce off atoms or get caught by electromagnetic fields. Second, their masses are so small that they zip around at near light speed, but not quite. And third, we're still not entirely sure how they gain their mass. They may interact with the Higgs field like other particles do, or there may be another unknown mechanism at play, perhaps even a completely separate Higgs-like field. The jury's still out. What makes neutrinos especially tantalizing is how their ghostly behavior could unlock secrets about the universe itself. Some researchers believe that neutrinos might help explain why there's more matter than antimatter in the universe. Others suspect they could be tied to dark matter, or at least point us in the right direction. They're like mysterious guests at a party who know all the gossip but never say a word. All of this brings us to a central truth about mass. It's not a one-size-fits-all property. Some particles carry mass and use it to shape the forces they mediate. Others are massless and travel freely, offering us windows into the cosmos. And then there are the in-betweeners, the neutrinos, so light they almost seem weightless, yet just massive enough to change their identity in flight. Each particle's mass, or lack thereof, tells a story. It tells us how that particle moves, how it interacts, how long it lives. The photon, with zero mass, never rests. It's always moving, always reaching. The W and Z bosons, heavy and constrained, flicker into existence only briefly. And the neutrinos, feather-light and fleeting, are still keeping secrets after decades of study. Even beyond the physics, there's something poetic about this particle tale. The ones that travel far and fast must shed their weight. The ones that act powerfully in close quarters must carry it. And the ones who barely whisper across the void are somehow both, and neither. At the heart of it all is mass, determining not just how heavy something is, but how it behaves, how it connects, how it shapes the fabric of reality. It's not just about scale or weight, it's about relationships. Whether a particle is massive or massless defines its role in the cosmic play, and every role, no matter how small, helps tell the story of the universe. Mass and matter. They often show up together in conversations, textbooks, and confused glances during physics class. The words sound like close cousins, and they're frequently used as if they mean the same thing. But in reality, they're quite different. One is the thing, the actual stuff that takes up space. The other is a property, a characteristic, a behavior. Understanding this difference is one of the great little unlocks in physics. Once you see it clearly, a lot of the universe starts to make a little more sense. Let's start with matter. Matter is what you might call the stuff of the universe. It's what you can touch, pick up, sip through a straw, or trip over in the dark. It includes atoms, molecules, particles, and anything composed of those building blocks. If it has a physical presence and occupies space, it qualifies as matter. Mass, on the other hand, isn't stuff at all. It's a trait, a number, a property that matter can have. But it isn't matter itself. Mass tells us how much inertia something has, how resistant it is to being pushed or pulled, how much it bends space-time. It's the quiet, ever-present signature that tells us how an object interacts with forces, but it's not the object itself. It's like flavor is to soup, or melody is to music. Real, measurable, but not something you can hold in your hand. You can have mass without having matter, and you can have matter with no mass, or at least very close to none. Take photons, for example. Photons are particles of light, and they are definitively not matter. They have no rest mass. You could chase one across the universe and never pin it down to a stationary state. Yet photons carry energy. They carry momentum. They can transfer pressure. They can push spacecraft equipped with solar sails and even knock electrons out of atoms in a photoelectric effect. But they are not matter, and they don't have mass in the traditional sense. This is one of those lovely little paradoxes that physics offers us. You might think intuitively that something without mass shouldn't be able to do much. But photons are deeply influential. They light up our world, warm our skin, and give plants the energy to make sugars. They obey the rules of energy and momentum, even without carrying mass. Their lack of rest mass is actually what allows them to travel at the speed of light. No particle with mass can ever reach that speed. It would require infinite energy. But photons, born massless, exist permanently at that cosmic speed limit. They're not accelerated to light speed. They're created there and stay there. It's like they were handed a first-class ticket to the universe's fast lane from the very beginning. Matter, on the other hand, is made up of particles that do have rest mass, like electrons, quarks, and their various combinations into protons, neutrons, and atoms. These particles can be still. They can lounge on a shelf. They don't need to be zipping around at the speed of light to exist. That rest state is part of what defines them, and their mass influences everything about how they behave, from how they fall, to how they collide, to how they bind together into molecules. But mass isn't the same as amount. A cloud can have more matter than a stone, but less mass, depending on how densely that matter is packed. A handful of uranium has far more mass than the same volume of feathers. It's not about how much stuff you can see, it's about how much resistance to motion and gravitational influence that stuff contains. Then there's energy. Remember that famous equation, E equals mc squared? It tells us that mass and energy are interchangeable. If you have mass, you have energy. And if you have energy, you have something that behaves like mass, even if it doesn't come in the form of matter. This leads to all sorts of fascinating consequences. A box of light bouncing around inside a mirrored cube would weigh slightly more than an empty cube, even though the light isn't matter. The energy of the trapped photons contributes to the system's overall mass. It's a perfect demonstration of how mass is a property that emerges from energy, not necessarily from stuff. In fact, most of the mass inside your body doesn't come from the actual matter, the particles you're made of. The mass of a proton, for example, is much greater than the sum of the masses of its constituent quarks. The extra mass comes from the energy of the strong nuclear force that holds those quarks together. In that sense, the majority of your mass is energy, bound up in motion and interaction, not in matter itself. So mass, it turns out, is more like a shadow cast by energy in motion. It tells us how strongly something will resist a push, how much it will bend space-time, how heavily it will sit on a scale. But it's not a substance. You can't pour mass into a cup. You can't scoop it with a spoon. It's a characteristic, not an ingredient. This distinction becomes especially important when dealing with things like dark matter. We call it matter because it appears to exert gravitational influence. It seems to have mass. But we don't know what it's made of, or if it even consists of particles in the traditional sense. If we eventually find that dark matter is just an exotic kind of energy behaving as mass, we might have to rethink what counts as matter entirely. And what about light pressure? Photons don't have mass, yet they can exert force. When light hits a surface, it transfers momentum, not because it has mass, but because it carries energy. It's another delightful demonstration that mass and matter don't always walk hand in hand. In everyday language, we tend to blend all these concepts. When you say something has a lot of mass, you probably picture a big chunk of matter. And that's fine. It works for practical purposes. But at the fundamental level, physics likes to be precise. Mass is how much inertia or gravitational pull something has. Matter is the substance that occupies space. And energy is what moves, binds, radiates, and sometimes even pretends to be mass for a while. You might think of matter as the furniture of the universe. Mass is how hard it is to push that furniture around, and energy is the party guest who keeps rearranging everything when no one's looking. This separation also helps clarify why some fields and forces act only on certain things. The Higgs field, for example, couples with particles that have mass. That's why photons ignore it completely. Gravity, on the other hand, is more democratic. It acts on energy, mass, and even light, bending the path of photons as they pass by massive objects. That's why starlight curves around galaxies, and why black holes can trap light. Understanding the difference between mass and matter opens up a more nuanced view of the universe. It reveals the roles particles play, the forces they feel, and the ways they interact with fields and energy. It clears up confusion and lets us appreciate just how strange and elegant our universe really is. So while your morning cup of coffee may be filled with matter, its mass is something subtler. It's not just the coffee beans and cream. It's the dance of particles and energy inside, each resisting motion just a little, each tugging on gravity with quiet insistence. Mass isn't what your coffee is. It's how your coffee behaves in a universe ruled by forces and fields. Matter is the actor. Mass is the role it plays. Imagine trying to weigh a whale by watching the ripples it makes in the ocean. You can't see it directly, can't touch it, and certainly can't fit it on a scale. All you have are the waves it leaves behind. Strangely enough, this is exactly how we weigh the universe. Galaxies, clusters, superclusters, they're far too massive, far too distant, and far too stubborn to step onto a cosmic bathroom scale. So instead, we watch the ripples they leave behind in space, in light, and in motion. When it comes to weighing celestial bodies, gravity is our go-to tool. It's invisible, unbreakable, and universal. Every object with mass pulls on every other object. That pull causes motion. And by studying motion, how stars orbit, how galaxies cluster, how light bends, we can infer the mass that must be behind it all. It's a bit like watching leaves swirl in the wind and figuring out the shape of the breeze. Let's start with galaxies. When astronomers observe a galaxy, they can measure how fast stars are orbiting around its center. These orbital speeds tell us how much gravitational pull the stars are feeling. And from that pull, we can calculate how much mass must be inside the galaxy to hold everything together. The logic is clean and elegant. More mass equals stronger gravity equals faster orbits. But here's where things get weird. When astronomers first did this in the mid-20th century, they expected to find that stars at the edges of galaxies moved more slowly than those near the center, just like planets in our solar system. But they didn't. Instead, stars far from the galactic core were moving just as fast as those closer in. In some cases, even faster. It was as if something invisible was tugging on them, holding them in orbit. Something with mass, but no light. This led to one of the biggest mysteries in modern astrophysics, the missing mass problem. The stars, gas, and dust we can see simply don't account for the gravitational effects we observe. In galaxy after galaxy, there appears to be far more mass than meets the eye. This hidden material, this unseen gravitational influencer, was eventually dubbed dark matter. Dark matter doesn't emit light. It doesn't absorb light. It doesn't bounce light around like ordinary matter does, but it definitely interacts with gravity. And so, although we can't see it directly, we can weigh it. We know it's there because of how it affects the motion of stars, the behavior of galaxies, and even the structure of the universe itself. Beyond individual galaxies, we can also weigh entire clusters, massive groupings of hundreds or even thousands of galaxies bound together by gravity. The same technique applies. Observe how galaxies move within the cluster. Calculate the gravitational forces required to keep them from flying apart, and then deduce the mass. And once again, the numbers don't add up. The visible matter accounts for only a small fraction of the total mass. The rest is something else. But motion isn't our only tool. One of the most elegant and mind-bending methods for weighing the cosmos involves watching light bend. This is called gravitational lensing. When light from a distant object, like a galaxy or a quasar, passes near a massive object such as another galaxy or a cluster, the gravity of the closer object bends the path of the light. It's like looking at a faraway candle through the bottom of a wine glass. The light curves, distorts, sometimes even creates multiple images. This bending happens because mass warps space-time itself. The more mass, the more curvature. So by measuring how much the light bends, we can estimate how much mass the light must have passed by. And gravitational lensing doesn't care what kind of mass it is, normal matter, dark matter, or something in between. It's beautifully unbiased. In some cases, the lensing effect is strong enough to produce dramatic visual features. Einstein rings, arcs, duplicated galaxies. These are cosmic art pieces created by pure geometry and invisible forces. But even in more subtle cases, Where the distortions are tiny, we can use them statistically, analyzing thousands of galaxies to build mass maps of the sky. These maps reveal the underlying distribution of matter, both visible and dark, on a scale that's simply breathtaking. One particularly famous example is the Bullet Cluster, a collision between two galaxy clusters. The gas from the clusters, which makes up most of the visible matter, gets slowed down and heated during the crash. But gravitational lensing shows that most of the mass doesn't follow the gas. It zooms straight through, barely interacting. This strongly suggests that the bulk of the mass is not ordinary matter, but something else, something dark, something that doesn't bump, scatter, or glow. It's one of the most compelling pieces of evidence that dark matter isn't just a miscalculation. It's a real, tangible part of our universe. To understand just how much mass is missing, consider this. In a typical galaxy, the visible stars, gas and dust make up only about 15% of the total mass. The other 85%? Completely invisible. Dark matter dominates the mass budget of the universe, outnumbering the stuff we can see nearly 6-1. And yet, despite decades of searching, we still don't know exactly what it is. We do, however, know that it matters. Dark matter shapes the large-scale structure of the cosmos. It forms vast halos around galaxies, dictating their formation and evolution. It clumps into filaments and nodes, creating a cosmic web that galaxies follow like ants along invisible trails. Without dark matter, the universe would look very different. Galaxies might not form at all, or they might collapse too quickly, never giving rise to stars, planets, or late-night physics videos. There are other ways to weigh the universe too. The cosmic microwave background, the afterglow of the Big Bang, carries subtle ripples that encode information about the density of matter in the early universe. By analyzing these ripples, scientists can infer the total mass-energy content of the cosmos and how it has evolved over time. All of these tools, orbital motion, gravitational lensing, background radiation, give us overlapping, converging lines of evidence. They tell a consistent story. Most of the mass in the universe is not in stars or planets or glowing gas. It's in something dark, silent, and pervasive. Something we can't see, but can feel through its gravitational pull. And yet, even with all this unseen mass, the universe is still surprisingly lightweight in cosmic terms. Space is mostly empty. Even galaxies are mostly empty. If you took the sun and shrank it to the size of a tennis ball, the nearest star would be another tennis ball over 700 kilometers away. The mass of the universe is immense, but it's also incredibly spread out. So how do we weigh the cosmos? We do it with mathematics, with light, with motion, with patience. We do it by listening to the whispers of gravity and watching how the universe bends and sways. We do it by accepting that sometimes the most important parts of the picture are the ones we cannot see. Mass, in the end, is not just about what's visible. It's about what matters. And in a universe where the brightest stars make up only a sliver of the total story, the mass we can't see might just be the most important mass of all. There is something out there. It doesn't glow. It doesn't reflect. It doesn't make a sound, doesn't scatter light, and doesn't seem to care about our telescopes, no matter how advanced they are. And yet, it shapes galaxies, bends starlight, and holds the universe together with a kind of quiet insistence. This is dark matter, the invisible mass that outnumbers all the shining stars, planets, and clouds of gas combined. At first glance, the idea of something you can't see making up the majority of the universe sounds suspiciously like a cosmic prank. But dark matter isn't a guess pulled out of thin air. It's a serious solution to a serious problem. The motions of stars, galaxies, and clusters simply don't make sense without it. There's a gravitational imbalance, a tug without a visible tugger. The math demands more mass than we can find. The first hints came from spiral galaxies. These majestic, swirling structures of stars and gas rotate like giant pinwheels. You'd expect that the stars closer to the center would orbit faster. After all, that's what happens in our solar system. The inner planets zip around the sun quickly, while the outer ones take their time. But when astronomers looked at the rotation curves of galaxies, graphs showing how fast stars move at different distances from the center, they found something strange. The speeds didn't drop off with distance. They stayed constant, sometimes even increasing. The stars in the outer regions were moving far too fast to be held in place by the visible matter alone. According to Newtonian physics, they should be flinging off into space, but they weren't. The only explanation that fit the delta was that there has to be more mass, something invisible, surrounding each galaxy in a vast spherical halo. Not just a little extra mass, but several times more than what we could actually see. It was as if galaxies were floating inside gigantic bubbles of hidden weight, and those bubbles were doing most of the gravitational heavy lifting. More evidence came from galaxy clusters. These are enormous gatherings of galaxies bound together by gravity. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster and found that the galaxies inside were moving far too quickly to be held together by the visible mass of stars and gas. He coined the term dunkle Materie, dark matter, to describe the missing mass that must be keeping the cluster intact. At the time, his ideas were largely ignored, but as decades passed and more observations rolled in, his early insights started to look more and more prophetic. Then came gravitational lensing, one of the universe's most poetic tools. When light from a distant galaxy passes near a massive object, like another galaxy or a cluster, it bends. The gravity of the nearer mass warps space itself, distorting the light's path. By studying the shapes and positions of these bent images, scientists can calculate how much mass is causing the effect. And time and again, the numbers reveal far more mass than can be accounted for by the visible matter alone. It's like watching shadows dance on the wall and realizing there are more people in the room than you thought. The Bullet cluster, one of the most striking pieces of evidence, shows two galaxy clusters that have collided. During the collision, the gas from each cluster, visible through X-ray telescopes, slowed down and piled up due to friction. But the mass, as measured by gravitational lensing, passed straight through. The lensing map and the gas map don't line up. The mass is clearly somewhere else. This shows that the majority of the mass in the clusters isn't in the hot gas, which is most of the normal matter. It's in something else, something that doesn't interact much except through gravity. So what is dark matter? That's the billion-dollar question. The truth is, no one knows for sure, but there are plenty of educated guesses. The leading idea is that dark matter is made up of particles, new kinds of particles that don't interact with light or electromagnetic radiation. These hypothetical particles would have mass, feel gravity, and maybe the weak nuclear force, but not much else. One popular candidate is the WIMP, short for weakly interacting massive particle. As the name suggests, WIMPs are expected to have mass and to interact only weakly with regular matter, making them incredibly difficult to detect. Another idea is axions, incredibly light particles that could form a kind of background field pervading the universe. Or sterile neutrinos, a cousin of the regular neutrino that's even more aloof and elusive. Or something we haven't thought of yet, a totally new category of physics hiding in the gaps of our understanding. Whatever it is, dark matter is not just a rounding error. It makes up about 85% of the matter in the universe. It plays a crucial role in how galaxies form and evolve. Without it, the delicate balance of cosmic structure would fall apart. Galaxies might never have coalesced in the first place. Stars might not have gathered into orbits. Planets, let alone people, might never have had a chance to form. Despite its mysterious nature, scientists have been trying hard to catch it in the act. Deep underground laboratories have been built to detect the rare interactions of dark matter particles with normal matter. These experiments sit quietly, shielded from cosmic rays and background noise, waiting for a single tiny ping that might reveal a passing WIMP. So far, the silence has been deafening, but not discouraging. If dark matter is real, and we're pretty sure it is, it's out there somewhere, hiding just beyond our reach. There's something poetic about that. The idea that the bulk of the universe's mass is made of something we can't see, touch, or hold. It suggests that visibility is not the same as importance, that some of the most influential players in the cosmic game are the ones backstage, pulling strings without stepping into the spotlight. And dark matter isn't alone in its mystery. It shares the stage with dark energy, a different, equally puzzling phenomenon that seems to be accelerating the expansion of the universe. Together, Dark matter and dark energy make up roughly 95% of the universe. That's right. Everything you've ever seen, touched, or known about, from stardust to sandwiches, is part of the remaining 5%. It's humbling, and also a little thrilling. To think that most of what exists is still beyond our understanding, that the universe has secrets, that mass can be present without being visible, powerful without being loud. Dark matter invites us to look more carefully, to question what we think we know, to search for fingerprints in the gravitational fabric of space, and to trust that the invisible is not the same as the non-existent. It reminds us that our cosmic scales measure more than just the obvious. They weigh the quiet things too. In the end, dark matter is less about darkness and more about mystery. It's a puzzle piece without a picture, a shadow without a form, but it's also a promise that the universe still holds wonders waiting to be revealed, patiently, silently, massively. Let's take a breath and shrink ourselves down, not just to the size of a dust mote or a single atom, but smaller still, past electrons and protons, into a realm where the rules of the everyday dissolve and space itself begins to shimmer with uncertainty. Welcome to the quantum realm, where particles are not tiny marbles but excitations of invisible fields, and where mass, strangely enough, is not something a particle simply has, but something that emerges from the very fabric of the universe through a delicate web of interactions. To begin, imagine space not as empty, but as a restless ocean, flat on average perhaps, but always rippling slightly if you look closely enough. In modern physics, every type of particle is associated with a quantum field that stretches throughout all of space. These fields are not optional features, they are the canvas on which all of reality is painted. And particles, they're ripples in those fields, tiny packets of energy, like drops jumping up from a calm puddle when a breeze rolls through. An electron then is a ripple in the electron field. A photon is a ripple in the electromagnetic field. These aren't just poetic comparisons, they're the literal description of what particles are in quantum field theory. When you see a particle, you're really seeing a little localized wiggle in a field that stretches across the entire universe. But what about mass? Where does that come from? In classical physics, mass is just a number, an input. In Newton's laws, you plug it in and carry on. But in the quantum world, mass is more like an outcome. It's a consequence of how a field behaves, its tension, its interactions, the way it couples with other fields, like the Higgs field we've already met. Think of mass not as a label on a box, but as a property that emerges from the dance of countless hidden influences. One of the strangest and most important contributors to this dance is the quantum vacuum. You might picture a vacuum as truly empty space, a barren expanse of nothing. But in quantum physics, the vacuum is more like a bubbling cauldron of activity. It is never truly at rest. Even when nothing is there, fields are still fluctuating, jittering with uncertainty due to the Heisenberg uncertainty principle. These fluctuations give rise to what are called virtual particles, temporary blips that appear and vanish so quickly they can't be directly observed, but their effects can be felt. These virtual particles are like passing thoughts in the mind of the universe. They're not permanent, but they influence everything. A particle like a proton sitting quietly in space is never truly alone. Around it, for the briefest instants, pairs of virtual particles are popping into existence and interacting with it. These ephemeral interactions contribute to the particle's mass, not by adding substance, but by altering how it moves through its field. It's a kind of quantum drag, a constant hum of influence that subtly changes the behavior of real particles. It's like trying to walk through a room filled with people whispering just out of earshot. You're still moving, but the whispers tug at you, change your pace, make your path less smooth. The virtual particles are those whispers, unseen, intangible, but absolutely real in their effect. Another calming metaphor. Picture a boat on a lake. The boat represents a particle. The lake is the quantum field. Even when the water looks still, there are ripples beneath the surface, fish jumping, reeds brushing, unseen currents flowing. As the boat moves, it doesn't just glide. It interacts with the entire system. Its movement depends on the hidden ripples beneath it. This interaction, subtle and persistent, is the origin of mass in the quantum realm. Quantum chromodynamics, or QCD, gives us another perspective. QCD is the theory that describes the strong nuclear force, the force that holds quarks together inside protons and neutrons. It turns out that most of the mass of these particles doesn't come from the quarks themselves. In fact, quarks are very light. Instead, almost all the mass of a proton comes from the energy of the strong force binding the quarks together. The glue that holds things in place, paradoxically, is the mass. It's like building a house from featherweight materials, but then using so many nails, bolts, and beams to keep it standing that the weight of the structure ends up being almost entirely in the supports. The energy of the glue becomes the mass of the thing it's holding together. That's the quantum world for you. Logic turned sideways, but consistent and breathtaking in its elegance. In this realm, particles are also not confined to being just particles. They can behave like waves too. Not metaphorical waves, but real mathematical wave functions. Patterns of probability that describe where a particle might be found. The mass of a particle influences the shape of its wave function, the way it spreads out or localizes. Heavier particles tend to be more tightly localized, while lighter ones are more diffuse. The mass determines how sharply reality focuses its lens on a particle's location. All of this becomes even stranger when we realize that the quantum fields themselves can have energy, even in their lowest possible state, the vacuum state. This vacuum energy may contribute to the overall mass energy of the universe, possibly even influencing its rate of expansion. It's like finding out your house, sitting quietly on its foundations, is resting on a trampoline that gently bounces with the heartbeat of quantum fluctuations. These ideas might sound too abstract, but their consequences are tangible. They help explain why particles have the masses they do, why electrons are lightweight, while top quarks are astonishingly heavy. Why the Standard Model, our best working theory of particle physics, holds together the way it does, and why, even in what appears to be nothingness, there is always something, a shimmer, a ripple, a quiet hum. Of course, the quantum realm is also a place of deep mystery. We can calculate mass from interactions, predict it from theory, and measure it in experiments. But we still don't fully know why each particle has that mass and not another. The electron is about 2,000 times lighter than a proton. Why? The top quark is heavier than an entire gold atom. Why should that be? These are questions we still ask, gently and persistently, while we stare into the equations. Some physicists suspect that deeper principles are at play, perhaps new symmetries, hidden dimensions, or even a multiverse where masses vary from one universe to another. Others look to theories like supersymmetry, string theory, or grand unification to offer clues. But even with our current understanding, quantum field theory gives us an astonishingly powerful toolkit. It doesn't just describe particles, it describes the very way that space gives rise to mass, as if mass were a tune played on the strings of an invisible cosmic harp. And so we return to that calming image of a ripple, a gentle disturbance in a silent field, stretching forever, connecting everything. In this view, mass is not a burden or a thing, but a whisper between fields. It is the language of motion, the consequence of presence, the stillness that follows a ripple once the lake settles. Here, in the quantum realm where every particle is a wave, every vacuum is a sea, and every moment buzzes with invisible life, mass is no longer just a number. It is the echo of energy, the geometry of interaction, the quiet weight of being something rather than nothing. And perhaps that's what makes it so beautifully strange. Even the most grounded property, mass, emerges from something that never stops moving. Empty space is one of those things we all assume we understand. It's nothing, right? The absence of stuff, the gap between planets, the quiet between stars, a vacuum. You picture it as cold, dark, and profoundly uneventful, a kind of cosmic storage closet with the lights off. But in physics, empty space has a reputation for being sneakily complicated. The more closely we examine it, the more it begins to misbehave. It shifts, it wiggles, it contributes energy, and yes, it might even carry mass. Sort of. Let's begin gently. Imagine empty space as a perfectly cleaned countertop. No crumbs, no coffee rings, no dust. Now imagine looking closer with a magical microscope. Under high enough magnification, what seemed flat and calm begins to shimmer. Little fluctuations ripple through, particles appear and vanish, fields buzz with activity. This isn't a dirty countertop. It's a quantum countertop. And in quantum field theory, even the vacuum, what we naively call empty space, is never truly empty. Every field in the universe, from the electromagnetic field to the Higgs field, fills all of space. Even when there are no particles present, the fields are still there, quietly humming away at their lowest energy levels. These lowest energy wiggles are what we call zero-point energy. It's the bare minimum buzz that never goes away, even when you've removed all the matter, all the heat, all the light. You can cool a system down, slow everything until it's as close to absolute zero as physically possible, but those quantum jitters remain. They are fundamental. Now here's where it gets fun. This zero-point energy is not just a mathematical curiosity, it has physical consequences. One famous example is the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, they will actually attract each other, ever so slightly, due to changes in the quantum fields between them. It's not that the plates are magically pulling on each other, it's that the quantum fluctuations of the vacuum are different inside the narrow gap than outside. The imbalance creates pressure. That pressure comes from nothing, from the vacuum. And that brings us to a question both beautiful and bewildering. If empty space contains energy, does it also have mass? According to Einstein's equation, energy equals mass times the speed of light squared. The answer appears to be yes. Energy and mass are interchangeable, so if space has energy, then it also contributes mass. But here's the twist. It's not mass in the usual sense. It's not something you can weigh with a scale or scoop into a jar. It's mass in the form of influence. It shapes the way gravity behaves. It curves space-time. This idea connects directly to the concept of the cosmological constant, first introduced by Einstein himself. Back in the early 20th century, Einstein was trying to make the universe behave. At the time, it was widely believed that the universe was static, neither expanding nor contracting. But gravity, left to its own devices, would pull everything together. To counteract this, Einstein added a term to his equations, a kind of built-in repulsion, a gentle outward pressure embedded in the fabric of space. This was the cosmological constant. It allowed for a universe that didn't collapse under its own gravity. Later, when observations revealed that the universe was actually expanding, Einstein reportedly called the cosmological constant his biggest blunder. But the idea didn't go away. In fact, it made a stunning comeback decades later when astronomers discovered that the universe isn't just expanding, it's accelerating. Galaxies are racing away from one another faster and faster, as if some invisible energy is pushing the cosmos apart. This mysterious push is now attributed to dark energy, a term that sounds like it belongs in a fantasy novel, but is very real. And the best current explanation for dark energy is vacuum energy, the energy of empty space itself. The cosmological constant may not have been a blunder after all. It may be the simplest way to represent the quiet but relentless expansion driven by the mass-like energy of space. Let's pause and consider how strange this is. Empty space, which we thought of as nothing, is actually full of energy. That energy gives it mass-like properties, and those properties shape the fate of the universe. The more space you have, the more vacuum energy there is. The more vacuum energy, the more outward pressure. And since space itself is expanding, there's more and more of it being created all the time. This leads to a kind of runaway effect, a gentle but persistent cosmic inflation. In some ways, it's like having a loaf of bread that grows more yeast as it rises. The more it expands, the more it wants to expand. It's not a dramatic explosion. It's more like a cosmic sigh, gentle, persistent, and impossible to stop. The idea that energy can exist without matter is one of the most counterintuitive in modern physics. We're used to associating energy with things, moving objects, burning fuel, sunshine, chocolate. But in quantum mechanics, energy is an intrinsic part of the vacuum. It's baked into the rules. And because of Einstein's equivalence, that energy contributes to gravity in the same way mass does. This also means that vacuum energy might help us explain one of the most perplexing questions in cosmology: why the universe is so flat. Not flat in a pancake sense, but geometrically flat, meaning that the angles of a large-scale space behave as expected, without extreme curvature. Vacuum energy may play a role in balancing the curvature, providing just enough pressure to counteract the gravitational pull of matter. Of course, none of this is completely settled. The precise amount of vacuum energy predicted by quantum field theory is vastly larger than what we actually observe through cosmology, by a factor of about 10 to the power of 120. This discrepancy is so enormous that it's often called the worst theoretical prediction in physics. It suggests that something fundamental is missing from our understanding. Either our math is wrong, or there are cancellations at work that we don't yet comprehend. Despite that, we can measure the effects. We see the acceleration of galaxies. We detect the subtle pressure of empty space. We know that the vacuum is not a passive backdrop, but a dynamic player in the universe's story. It adds mass-like influence without matter. It curves space-time without having atoms. It turns nothing into something. This concept stretches the boundaries of intuition, but it also invites a kind of quiet awe. The idea that mass can exist without substance, that energy can reside in nothingness, that space itself can act. These are not just abstract notions. They are the real behaviors of the universe at its most fundamental level. It also adds depth to our understanding of mass. We've followed mass from the weight of apples to the core of protons to the ripples of quantum fields, and now we find it, even faintly, in the very emptiness between galaxies. Mass is not always tied to matter. It's tied to energy, and energy, it seems, is everywhere. So the next time you picture the vast dark stretches between stars and galaxies, try not to think of them as voids. Think of them as quiet seas, gently humming with invisible ripples. Think of them as woven with potential, heavy with silent power, expanding steadily with each passing second. Empty space is not so empty after all. It is the universe's quietest mystery, and it carries more weight than we ever imagined. Time, we like to think, is universal, ticking along at the same steady rhythm for everyone, everywhere. 1 second is 1 second, whether you're sipping tea on the porch or orbiting the Earth at 8,000 meters per second. But as it turns out, time has a secret. It's not as steady as it pretends to be. In fact, time bends. It stretches and slows depending on where you are and how fast you're moving. And mass, that unassuming quality we've been following all this time, is one of the main reasons why. It's not that heavy objects carry little clocks that run slower. It's that mass changes the shape of space-time itself, and when space-time bends, time bends with it. Let's ease into this. Imagine space and time not as separate things, but as part of one big stretchy fabric, space-time. This fabric can curve, ripple, and dip in the presence of mass and energy. The more massive something is, the deeper the dip it creates in the surrounding space-time. Picture placing a bowling ball on a soft mattress. The mattress sinks under the weight, and anything that rolls by will curve toward the dip. Now imagine that same dip, but in time. Near a massive object like a planet, a star, or a black hole, time slows down compared to farther away. Not because anything is broken or lagging, but because the shape of time itself has stretched. This is gravitational time dilation, a phenomenon predicted by Einstein's theory of general relativity and confirmed by experiments again and again. And it's not just theoretical. We use this knowledge every single day, without even realizing it, every time we check our location on a GPS device. You see, the GPS system works by triangulating signals from satellites orbiting high above the Earth. These satellites carry extremely precise atomic clocks, ticking away with unbelievable consistency. But those clocks don't tick at the same rate as identical ones on Earth. Because the satellites are farther from the Earth's center of mass, they experience less gravitational pull, and thus time runs slightly faster for them. At the same time, the satellites are moving very quickly around the Earth, and according to special relativity, moving clocks tick slower than stationary ones. So there's a bit of a tug-of-war between these two effects. One makes the satellite clocks run faster, the other makes them run slower. When you crunch the numbers, gravitational time dilation wins. The net effect is that GPS satellite clocks tick about 40 microseconds faster each day than Earthbound ones. That might not sound like much, but if uncorrected, this tiny discrepancy would result in positioning errors of about 10 kilometers per day. Your GPS would think you're in the next town over, so the GPS system has to correct for general relativity, compensating for the bending of time by mass. It's a strange and beautiful example of how deep theoretical physics quietly helps us find our way to the grocery store. Gravitational time dilation isn't just a technical glitch, it's a window into the very nature of reality. It means that time doesn't flow at the same rate everywhere. Clocks tick more slowly in strong gravitational fields, and because mass creates gravity, that means heavier objects slow time down, not just metaphorically, literally. If you lived at the bottom of a deep well with a very precise clock, and someone else lived at the top with an identical clock, the person at the top would age slightly faster than you, not by much, but measurably. Experiments using high-precision atomic clocks placed at different elevations have confirmed this. Clocks on mountaintops tick a little faster than those at sea level. Even a height difference of just a few meters can make a difference in the ticking rate, though it's extremely small. But scale that up, and the effects become profound. Near a neutron star, where mass is incredibly concentrated, time slows dramatically. Near the event horizon of a black hole, time slows almost to a stop from the perspective of a distant observer. If you could somehow hover just outside a black hole and survive, time for you would pass incredibly slowly compared to the rest of the universe. Spend an hour there, and you might return to find that centuries have passed elsewhere. This isn't science fiction, it's science. The warping of time by mass is real, and it adds a subtle, poetic weight to the idea that heavy things move slowly, not just in space, but in time as well. Even our concept of simultaneity, of two events happening at the same time, breaks down in curved space-time. Because time stretches differently in different places, what's simultaneous for one observer may not be for another. Mass creates these differences by warping the fabric that time moves through. You might wonder, why does mass have this power? It all comes back to energy. Mass and energy are two forms of the same thing, and energy tells space-time how to curve. This is the core idea of general relativity. Mass energy bends space-time, and curved space-time tells objects how to move. Time and space are not passive backgrounds. They are active participants, shaped by the very things they contain. This relationship also flows the other way. If space-time were completely flat, no mass, no energy, no curvature, time would tick uniformly everywhere. But our universe is filled with stars, galaxies, and enormous structures. Mass is everywhere, and so time flows differently from place to place. It varies slightly on Earth, more noticeably near massive objects, and dramatically in extreme environments like the hearts of galaxies. There's something comforting in this quiet connection between mass and time. It links the tangible to the intangible. The stone on the ground bends the very flow of moments. The planet you're standing on subtly changes how fast the universe moves around you. Even your own body, though small, contributes its own infinitesimal curve to the vast tapestry of space-time. And this connection is more than just an interesting footnote. It's central to how we navigate the cosmos. Whether we're launching spacecraft, studying black holes, or syncing networks of clocks, we must account for the gentle pull of mass on time. We must remember that heavy things don't just anchor us in space, they anchor us in time as well. It invites a new perspective on something as familiar as gravity. We usually think of gravity as a force pulling objects together. But in general relativity, gravity isn't a force at all. It's the result of moving a long curved path through space-time. Mass tells time to slow, and space to curve, and everything else. Falling apples, orbiting moons, stretching tides, follows naturally from that. So the next time you glance at a clock, know that it's doing more than marking seconds. It's feeling the weight of the Earth. It's keeping pace with a rhythm that depends on the mass around it. It's not just ticking, it's adapting, stretching and slowing ever so slightly in a cosmic ballet choreographed by gravity. Time is not fixed, it's elastic, and mass is the hand that gently presses on the dial. Mass feels so simple at first. It's the heft of a rock, the burden of a suitcase, the thing your body puts into a chair after a long day. It seems solid, grounded, reliable. Yet the deeper we explore it, the more mass becomes a riddle, a property that emerges from invisible fields, a measurement shaped by energy, a participant in the warping of space-time, and ultimately a mystery still wrapped in equations and untested ideas. For all our progress, we still don't entirely know what mass is. We can measure it with precision, we can describe how it behaves, we can even trace its origins in quantum field theory, assign it to particles via interactions with the Higgs field, and watch it shape galaxies with quiet determination. But those answers are only partial. Mass remains one of the most fundamental properties of nature, and one of the least completely understood. One of the biggest challenges in physics is reconciling two beautiful but contradictory theories: quantum mechanics and general relativity. Quantum mechanics is the domain of the tiny. It governs particles, fields, and probabilities, where uncertainty is woven into the fabric of reality. General relativity, on the other hand, is our best description of gravity, the force that emerges from mass and energy curving space-time. It works wonderfully on large scales, stars, planets, the expansion of the universe, but they don't quite play well together. At small scales, at the heart of black holes or in the early moments after the Big Bang, these two descriptions clash. Quantum fields and curved space-time don't blend smoothly, and that means our current theories break down when we try to describe mass in those extreme primordial environments. We don't have a complete theory of quantum gravity, something that would unite these frameworks into one seamless picture of reality. Some physicists hope string theory may offer a path forward. In this view, particles aren't point-like, but tiny vibrating strings, each vibrating at a different frequency. Mass, then, is the musical note played by a string. It's a beautiful metaphor, and one that connects geometry, vibration, and identity in a single stroke. But string theory remains speculative. It's elegant, but so far untestable. Like poetry written in a language we haven't yet learned to speak. Others turn to loop quantum gravity, an approach that attempts to quantize space itself. In this vision, space is not continuous, but built of tiny loops woven into a kind of quantum fabric. Mass and energy become properties of this woven geometry. But here too the mathematics is complex and the experiments out of reach. We are feeling our way in the dark, brushing fingertips across a locked door. Even within the standard model of particle physics, the most successful framework we've ever constructed, there are nagging puzzles. Why do particles have the masses they do? The electron is roughly 2,000 times lighter than the proton. Why? The top quark is heavier than an entire atom of gold. Why such a spread? The equations allow these masses as inputs, but they don't explain where the values come from. They're just there. And what of dark matter? We know it has mass. We know it gravitates, but we don't know what it's made of, or how it fits into the broader picture of particle physics. Whatever it is, it may hold the key to understanding mass in a new light, possibly through a particle that hasn't yet been discovered, or through a force that lies just beyond our current instruments. There's also the puzzle of inertia. We know what inertia does. It resists acceleration, and we can calculate it using Newton's laws or Einstein's equations. But what causes it at the deepest level? Some have speculated that inertia might arise from the quantum vacuum, a sort of resistance generated by interactions with distant matter or with all of space-time itself. These are ideas still in development, hints rather than conclusions. In this way, mass becomes a philosophical playground as much as a physical one. Is mass something real, an intrinsic, unchangeable property of matter? Or is it emergent, a kind of illusion that appears only when particles interact with fields and forces. In physics, we often talk about effective properties, things that emerge from underlying complexity. Temperature, for example, is not something a single atom has. It emerges from the collective motion of trillions of particles. Could mass be the same? If so, then asking what mass is might be like asking what a rainbow is. It's not an object you can hold. It's a phenomenon that emerges from conditions: sunlight, water droplets, perspective. Mass, in this philosophical light, might be not a thing but a consequence, a whisper between particles and fields, a behavior, not a building block. Even the language we use can shape our understanding. We say, an object has mass, as if mass was something stuffed inside it. But maybe it's better to say, an object experiences mass, the way it experiences temperature or color. Mass is not what a particle carries, but how it participates in the story of the universe. And then there's time. As we've seen, mass curves space-time. It shapes the flow of time itself. That link between mass and temporal rhythm adds a metaphysical weight to the whole discussion. If mass can slow time, then mass isn't just a measure of how heavy something is. It's a measure of how deeply it rests in the universe. You begin to see that mass is not a number written on a label. It's a kind of signature, how a particle dances with the fields around it, how it moves through space, how it ages in time. Will we ever understand mass completely? Perhaps. Maybe a breakthrough in quantum gravity will stitch together the torn seams of our theories and reveal a deeper framework where mass is no longer mysterious. Maybe dark matter will point the way to new particles or forces that reframe the entire question. Or maybe the understanding of mass will remain forever, a little blurry around the edges, a mystery not because we're missing data, but because some things resist being boxed in. Physics has a habit of surprising us. The best answers often come when we ask a different kind of question, when we stop trying to weigh reality and instead listen for its rhythm. Mass in the end may be like the baseline of the cosmos, steady, grounding, and felt in everything else that moves. And perhaps the goal isn't to solve it like a riddle, but to understand it like a song, to feel its weight not just in the numbers but in the way the universe dances through time. Whether we fully understand it or not, mass is a quiet reminder that even the most familiar things, your chair, your breath, the earth beneath your feet, are bound into a story more strange, more elegant, and more unfinished than we could have guessed. A story still unfolding, one gravity-shaped second at a time. Massachusetts. It seemed so straightforward when we began. A quantity, a number, the thing that tells us how heavy something is, how stubborn it is to move, how it sinks a scale or keeps a planet in orbit. But along the way, it revealed itself to be so much more. Not a static measure, but a dynamic story. A quiet consequence of fields, of ripples, of energy playing out across the invisible threads of the universe. Every object you've ever touched, every stone, every spoon, every cup of tea, has mass. But that mass is not a lump of stuff inside it. It's the echo of deeper things. It's the resistance of motion through the Higgs field, the binding of quarks by the strong force, the dance of energy within particles, and the flicker of quantum fields that never sleep. Mass is the conversation matter has with the fabric of space. It is not what something is, but how it behaves in the presence of everything else. It emerges from motion, from interaction, from silence even. Empty space is not empty. The void, as it turns out, is brimming with potential. Vacuum energy hums beneath the surface, fields ripple even in the dark. And within that silence, mass quietly asserts itself, a weight not of substance but of presence. Even light feels the pull. Photons, massless and tireless, still respond to the mass of others. They bend around galaxies, trace curves across the sky, whispering of invisible matter as they go. Their paths sketch out the contours of mass we cannot see, showing us the gravity of absence. And through it all, time ticks differently, depending on where mass lies. A mountain, a planet, a black hole, they each change time's flow, not by force, but by gently reshaping the stage on which everything unfolds. Mass slows clocks. It bends paths. It gives the universe a kind of rhythm, a slowness where the cosmos leans inward. In the end, mass isn't a thing, it's a relationship. A particle's conversation with a field, a star's negotiation with space-time, a presence that curves the universe without ever raising its voice. It's the quiet pull that keeps galaxies turning, oceans rising, and your feet resting on the Earth. We may never fully understand it, not because it's unknowable, but because mass leads us deeper, always deeper, into realms where particles are waves, where time stretches and folds, where matter is less stuff and more a song that fields are singing. And still, mass holds everything together. It gives atoms their structure. It keeps stars burning. It gathers clouds of gas into galaxies, and galaxies into clusters, and clusters into the vast filaments of the cosmic web. Without it, there would be no planets, no people, no places to stand or stories to tell. It is the quiet architecture of being. So let's drift now through a universe filled with invisible weight. Let's float among the stars, where every point of light holds its place because of gravity's embrace. Let's pass through dark matter halos, gentle and unseen, holding galaxies together like thread in a needlepoint sky. Let's sail past the curving edge of space-time, where clocks slow and mass speaks in the language of time itself. You are part of this, your body, made of particles shaped by mass, your thoughts, ticking forward in a brain made of atoms, whose mass comes not from the matter itself, but from the binding, the motion, the dance of fields. Even in stillness, you are heavy with interaction, grounded by the quiet legacy of energy. So we return to those gentle questions we asked at the beginning. What is mass, really? Is it just a number, a measure, a property? Or is it something more? A footprint in space-time? A song between fields? A whisper of the universe's hidden structure? Maybe the answer is yes to all of it. And maybe that's the beauty of it. Mass, like wonder, grows deeper the more you look. It invites not just understanding, but reflection. Not just measurement, but awe. So if this journey kept you awake, let it be with curiosity. And if it lulled you gently towards sleep, let the last thing you feel be the soft weight of wonder. That everything, everywhere, from the dust on your windowsill to the furthest flicker of starlight, is held in place by something you cannot see but always feel. Thank you for drifting with me. And as always, I'd love to know, where in the world are you listening from tonight? What time is it where you are? If this story brought you a moment of peace, a glimmer of awe, or simply helped ease your mind into stillness, a like or a subscription would mean the world. Until next time, sleep softly. You are cradled by mass and held by the stars.